action potential. When a neuron is inactive, it is polarized. Intracellular cytoplasm has a negative charge, and the extracellular fluid has a positive charge. This separation of charge sets up conditions for the neuron to respond. The electrical difference across the membrane of the neuron is called its resting potential. The resting potential is created by a transport protein called the sodium-potassium pump. This protein moves large numbers of sodium ions outside the cell, creating the positive charge. At the same time, the protein moves some potassium ions into the cell's cytoplasm. Because the number of sodium ions moved outside of the cell is greater than the number of potassium ions moved inside the cell is more positive outside than inside. When a stimulus reaches a resting neuron, the neuron transmits the signal and an impulse is called an action potential. Excitable cells can be stimulated to create electrical currents and are the cells affected by action potential. During an action potential, ions cross back and forth across the neuron's membrane, causing electrical changes that transmit the nerve impulse. The stimulus causes sodium ion channels in the neuron's membrane to open, allowing the sodium ions that were outside the membrane to rush into the cell. The sodium channels are called voltage-gated ion channels because they can open and close in response to signals like electrical changes. When the sodium ions enter the neuron, also known as influx, the cell's electrical potential becomes more positive. If the signal is strong enough and the voltage reaches a threshold, it triggers the action potential. More voltage-gated ion channels open, allowing more sodium ions inside the cell, and the cell depolarizes so that the charges across the membrane completely reverse, and the inside of the cell becomes more positively charged and the outside becomes more negatively charged, and the activation gate is opened by depolarization. The peak voltage of the action potential causes the gated sodium channels to close, the inactivation gate, and the potassium channels to open. Potassium ions move outside the membrane, and the sodium ions stay inside the membrane, which repolarizes the cell. This result is a polarization that is opposite of the initial polarization that had sodium ions on the outside and potassium ions on the inside. The neuron becomes hyperpolarized when more potassium ions are on the outside than sodium ions are on the inside. When the potassium gate finally closes, the neuron has slightly more potassium ions on the inside than it has sodium ions on the outside. This causes the cell's potential to drop slightly lower than the resting potential, also known as the efflux. The neuron enters a refractory period, which returns potassium to the inside of the cell and sodium to the outside of the cell. The sodium-potassium pump goes back to work, moving sodium ions outside the cell and potassium ions inside the cell, returning the neuron to its normal polarized state.